This presentation is about penalized or regularized regression models. So what's the big idea behind these types of models? Well, we want to mitigate overfitting the model. And so to do this, we can add a penalty to the cost function so that the penalty increases as the model complexity increases. Therefore, we end up biasing the model towards a more simple model. So why would we want to do this? So remember, overfitting happens when the model learns the signal as well as the noise within the data to the point that the model is not able to generalize well on new data that it hasn't seen before. Overfitting tends to happen as you include more and more variables in your model. So what we are trying to do with regularization is we're going to add a penalty to the model so that as our model complexity increases, the penalty is going to increase as well. And the result is that you end up biasing your model towards a more simple model. In order to add clarity to our discussion of the cost function, we need to first review ordinary least squares. So the basic formula for a simple linear regression is shown here. And in this case, we would try to estimate y hat using our intercept beta naught and then the sum of our betas multiplied by our x variables. And then we try to fit these beta coefficients so that we end up minimizing the sum of squared errors, or SSE. And then the sum of squared errors ends up being our cost function. So what we're going to do with penalized regression is we're going to add a penalty to this cost function, just like before, but this time we'll minimize a different cost function. This portion here is our sum of squared errors like before, but then we're adding a regularization term that is then added to our cost function. So this p sub lambda of beta is the penalty function that we're adding. Let's review the different types of penalties that you can have. With ordinary least squares regression approach, we don't have a penalty. We just use the sum of squares error. You will not want to use OLS regression, obviously, when the assumptions are violated. For lasso, we have the penalty listed here that's added to our sum of squared errors. You will want to use this when there are sparse effects or you have a lot of different variables. Here we have the penalty for the ridge regression. You would want to use this when you have correlated predictors. You do not want to use it for variable selection. You instead want to use the lasso method for that. And then the penalty for the adapted lasso method is also shown here. This would be used when your number of predictor variables is higher than the number of your observations that you have. You don't want to use that when you have correlated predictors or when you have a saturated model. And then here at the bottom we have the elastic net type of penalty. And you don't want to use the adapted version with the correlated predictors. So in this discussion, we're going to focus on the lasso and the ridge regression. So now we're going to go into how we select the tuning parameter. And so in all of these models or penalties, you see that the penalty has a tuning parameter of lambda. This lambda parameter will then dictate how much of a penalty we're adding, and the approach that has been used to develop or identify the penalty is gradient descent. So the cost function basically tells us how good our model is at making predictions for a given value. And we're using this penalty in fitting a lambda, which is similar to the tuning parameter that is then dictating how much of a penalty is being added to our cost function. And then to go through an iterative process. It may randomly choose to start here at some lambda parameter, and then it goes through the process of gradient descent, which is using calculus functions to look at it to see if I make a small change to determine the system rate of change immediately to the right or to the left of the change that I make. So I'm trying to make it go lower, so it will choose the point where it is lower, and it will keep iterating until it converges to that global minimum. And then at that point, it will be used to identify the weight that we will use for our lambda parameter. LASSO stands for Least Absolute Shrinkage and Selection Operator. The lasso regression solves this regression model just as we've seen before. And then again, as a reminder of what we are doing here, we're adding a penalty to our cost function, which the cost function for regression is our sum of squared errors. We are adding this penalty, and then again, we have our lambda, which is the tuning parameter that we will use. Now, if lambda is 0, we'll then get back our ordinary least squared model. Whereas if the lambda parameter is large, it will make the coefficients 0, and therefore it underfits our model. And it's going to find the best fit that would minimize this cost function somewhere between ordinary squares regression model and then having all the betas equal 0. So lasso tends to eliminate the weights of the least important features by setting them to 0. And by doing that, you're actually performing feature selection because some variables will go down to 0, whereas the important ones will have very low weights assigned to them from a penalty perspective. Ridge regression, again, we are solving the same problem here, and we are adding to the cost function the sum of squared errors, which is this part. We're adding this particular cost function. Again, this is the lambda parameter, which is our cost function. And if lambda is 0, again, we get back to ordinary least squares regression. So, however, if lambda is really large, then it will add too much weight and it will lead to underfitting our data. The key difference between lasso and ridge regression is that lasso shrinks the less important features down to 0. Therefore, it's going to remove the feature altogether. Lasso works well for feature selection when you have a large number of features because it will set some of them to 0, therefore taking them out of the model. Ridge regression will always keep them. It will just assign a low weight to the features that are not important in your model. Another approach that you can use is the elastic net, where this is what you're trying to minimize with your elastic net. You can think about it as a hybrid of ridge and lasso approaches, where the alpha controls how much of each model is being used. You are combining the elements of ridge and lasso with the parameter alpha, and alpha is going to dictate how much of each model you end up using. The idea with adaptive methods is if we could somehow know which factors are active and useful in advance, we could penalize them less. And we know the ordinary least squared estimates. And what we can do is weight the penalty by the inverse of the OLS estimate, and then it is useful for variable selection, but not useful for prediction. So in this discussion, we'll not really be using adaptive methods. And then adaptive methods can fail when predictors are strongly correlated, which is more likely to happen when we have many predictors in our modeling types of problems. So once again, that's why it's not really very useful in our case. Now, how do we go about assessing the goodness of fit for generalized regression models? Well, similar to other models, we use a validation column to assess how well the model performs on that data that it's not seen before. By creating a validation set that identifies training and then the test data set. You can also apply k-fold cross-validation and several statistical packages, depending on what you use. They can select a random holdback set for you so that you can use that random holdback to be able to divide your data into your testing and validation set. So what are some advantages of a penalized regression model? Linear predictors are easy to understand and interpret. You are still working with a linear predictor just like we had before with a linear regression. The approach works well for categorical and continuous variables or targets. It provides variable selection techniques. As we discussed, the lasso will actually identify those most important variables and will only keep those within your model that you need and effectively weight all the non-important ones down to 0. It's going to handle correlated and high dimensional inputs very well and allow for the specification of the distribution of the target variable as well, which can be pretty useful. And several penalization methods are available, as we've discussed here. Future discussions will focus on ridge regression and lasso regression, which are going to be the two most widely used ones in this case. So, what disadvantages do we have for penalized regression? Well, it's not as well known as other techniques, and the choice of penalization method may not always be clear, and choosing a method always includes some level of judgment. When polynomial model forms are used, it might not have enough flexibility, and it's also unclear how to determine the advanced controls of the methods. And sometimes it's also difficult to tune the models themselves. And it can also fail when you have the number of observations in your model is far fewer than the number of predictors that you have in your model.